Next section that we'll look at is titled Pascal's Triangle. Pascal's triangle is a definition or table that we'll use to solve problems in the next section. To start off Pascal's triangle, we'll start with the single number 1, and underneath of that we'll put 2 more 1s. This 1 is considered the first row, these 2 1s are considered the second row, and we'll continue down and we'll do 9 total rows for Pascal's triangle. To get the third row, what we'll do is take the 2 numbers above, 1 and 1, add those together, which will get us 2 for the third row. The outside numbers will be 1s. So our first row would be 1, our second row would be 1 and 1, our third row would be 1, 2 and 1. For the next row again, we take 2 numbers above, 1 and 2, add that, and it goes in between the 2 numbers for the next row. We also have 2 and 1 over here. We can add those to make a 3. And to make the triangle shape, always put a single 1 on each side. And again, now we have 4 rows. We will continue down until we have 9 rows. 1 plus 3 would be 4. 3 plus 3 would be 6. 3 plus 1 would be 4. And the single 1s on the outside to continue the triangle shape. 1 plus 4 would be 5. 4 plus 6 would be 10. 6 plus 4 would be 10. 5 and the 2 1s. The next row would be 6, 15, 20, 15, 6, and 1 on both sides. Next row would be 7, 21, 35, 35, 21, 7, and 2 1s. This last row that we did, that would be row 1, 2, 3, 4, 5, 6, 7, 8, and we'll continue on to do one more. That would be 8, 28, 56, 70, 56, 28, and 8, with 2 1s on each side. This will be Pascal's triangle for 9 rows. You could continue on the triangle. I'll put ... because you can do as many rows as you need to solve different problems. Couple patterns on Pascal's triangle. Each row increases by 1 number. The first row has 1 number, second row 2 numbers, third row 3 numbers, fourth row 4 numbers. So the 9th row would have 9 numbers. Also, the triangle is perfectly symmetrical. Whichever number you have on one side, you have the same number on the other side. Section we'll use Pascal's triangle for is titled Using Pascal's Triangle. The definition for this one is we will use row exponent plus 1. So in these questions, whatever the exponent is, we'll add 1 to that, and that's the row that we'll use for Pascal's triangle. First question, and only question for this section, is expand x plus y to the 7th power. To actually solve this algebraically, x plus y, you'd have to write 7 parentheses with x plus y, go through and FOIL each one out until you come up with the polynomial for the answer. The shortcut method is we can use Pascal's triangle, and we'll use row exponent plus 1, the exponent 7, so we'll be using row 8. Looking back at Pascal's triangle, row 8, if we write just the numbers down with commas, it would be 1, 7, 21, 35, 35, 21, 7, and 1. To get the answer for the expansion of x plus y to the 7th power, we'll take the first number, which is 1, followed by the first variable, which is x. The exponent will be the exponent originally in the question, which is x to the 7th, followed by y. The second variable will always start with a 0 exponent. And this will be our first term in the sequence, 1, x to the 7th, y to the 0. And then plus our second term will be the second coefficient or second number, which is 7. The exponent on the x will decrease by 1, x to the 6, while the exponent on the y will increase by 1, y to the 1st. Plus the third term, we'll use the third number 21. And again, we'll take x, decrease by 1, which would be 5, and the y exponent increases by 1, which will be 2. We will continue this pattern for all the numbers in row 8. After 21, we'll have 35. X will decrease by 1, x to the 4th. Y increases by 1, y to the 3rd. The next number, 35 again. X will decrease by 1, and y will increase by 1. Plus 21, x squared, y to the 5th, plus 7, x to the 1st, y to the 6th, and our last term, plus 1, x to the 0, y to the 7. All these terms will be our final answer for the expansion of x plus y to the 7th power. A couple patterns about this. Again, the numbers are symmetrical. We'll have 7s and 7s, 21s and 21s from the Pascal's triangle. Also, if you look at every exponent, every term, they all add up to 7. And you should begin with the exponent 0, and you should also end with an exponent 0. The 0 exponents we can cross off and ignore, because y to the 0 and x to the 0 is equal to 1. And also, if you wanted to, you could take off the 1 coefficients and just have x to the 7th and y to the 7th. Title of the last section today is Find a Particular Term. The equation for this section is combination C n comma r times a to the exponent of n minus r times b to the exponent of r. Combinations we did in the previous chapter, the probability chapter. The two variables on this one, n is equal to the exponent, which will be given in the problem, and r is the term number minus 1. So whatever the term number is, take away from 1 from that, and that's what r would be. The combination formula that we did in chapter 12 is n factorial divided by n minus r factorial divided by r factorial. A and b will be the variables given in the equation. The first problem for this section, find the fifth term of the quantity x plus y to the exponent of 10. What we can do for this problem, instead of expanding this out using Pascal's triangle and finding the fifth term listed, we can use the rows and the other numbers. For this question, we have combination n comma r. N again is the exponent in the question, which would be 10. R is the term number. We're looking for the fifth term, but term number minus 1, which should be 4. So we'll have combination 10 comma 4. And we'll multiply. Instead of a, we'll use the first variable, which is x, to the n minus r power, which would be 10 minus 4. And instead of b, we'll use the second variable y to the r power, which would be 4. Solving this, combination 10 comma 4 would be 10 factorial divided by 10 minus 4 factorial, which would be 6 factorial. Also divided by r, which is another 4 factorial. And we'll have x to the 6th power and y to the 4th power. Multiplying out the factorials, 10 factorial is 10 times 9 times 8, all the way down to 1. And 6 factorial is 6 times 5, down to 1. And 4 factorial is 4 times 3 times 2 times 1. Solving this, the 6 through 1 we can cancel in the numerator and denominator. We can also cancel the 8. 4 times 2 would be 8, and that would cancel the 8. And the 3 we can divide into the 9. So the numerator will be left with 10 times 3 times 7, which would be 210. Bringing our exponents down, x to the 6th, y to the 4th, we would have our answer of the fifth term of the expansion x plus y to the 10th power. The fifth term would be 210, x to the 6th, y to the 4th. Second question we'll look at. Find the fourth term of x minus 2 to the exponent of 7. And again, we'll have combination n, which is the exponent, in this case is 7, and r is the term number 4 minus 1, which would be 3. And instead of a from the equation, we'll use x. N minus r, which would be 7 minus 3. And instead of b, we'll use the number 2. Has a negative sign, so we'll use a negative 2 to the r exponent, which would be 3. Multiplying out, 7 combination 3 would be 7 factorial divided by 7 minus 3, which is 4 factorial, and 3 factorial. X to the 4th, and negative 2 to the 3rd would be negative 8. 7 factorial, 7 times 6 times 5, all the way down to 1. And 4 factorial, and 3 factorial. 4, 3, 2, 1 we can cancel. And also 3 times 2 would be 6, so the 3, 2, and 6 would cancel. We'll be left with 7 times 5, which is 35. We have x to the 4th, and we also have negative 8. Since we have a number as our last term, and we have 35, we can combine those, and that would be negative 280, x to the 4th. So the fourth term of the sequence, if we'd use Pascal's triangle to write out all the terms, the fourth term would be negative 280 x to the fourth.